Okay, welcome to part 2 of the function toolkit, and away we go. We are going to examine exponential and logarithm functions in this new section of function toolkit. So basically what's happening here is you're dealing with things that are a lot more recent, except that in 12a we didn't really get to much graphing or anything like that. Okay, so you can almost consider this section of function toolkit to be an extension of the log unit that you already have completed in 12a. So basically, okay, we're dealing with two different types of graphs. So we have the exponential function up top here, which is any number to the power of x. So we're gonna keep things a little bit simpler by just dealing with growth curves, increasing curves, meaning the number that's to the power of x has to be greater than 1. And then we're going to deal with a specific example of those graphs where we have e to the power of x. And just a reminder that e is a special mathematical number that's approximately equal to 2.718. Again, it's greater than 1, so it's going to have the same type of graph, original graph. And notice that the original exponential function has a key point of 0, 1, unlike in part 1, all of those graphs that we did in the previous section had a key point of 0, 0. So that's one thing that's different. And also, for the first time, we're dealing with asymptotes. So we have a horizontal asymptote of y equals 0. And of course, that can shift up or down. That's going to change with the vertical translation. And then also in some other videos that are coming up, we're going to deal with logarithm graphs, which has a key point of 1, 0 and has a vertical asymptote. So we're going to deal with log of x graphs and then a specific type of log graph, which is ln, natural logs, which is really just a log with a base e. And away we go. Okay, let's do this. This is going to involve some graphing, which is kind of new. It's also going to involve some algebra of logs and exponents, some things that you have dealt with in the unit previous in 12a. All right, so let's just get started with this. We're going to take a look at one example in this video. This is an exponential function. So first of all, okay, one thing that we want to make note of here is that the 2 that's in that equation, that does not go into the mapping notation. Okay, 2 is part of the original function, so we're going to have y is equal to 2 to the x as the original function. In other examples, you're going to have a 3 or a 4, usually one of those numbers. That's not going to change, okay? So the number that's to the power of x won't show up in your mapping notation. It's part of the original function, which once again looks something like this. It's a growth curve with a key point at 0, 1 and a horizontal asymptote of y is equal to 0. So when we do our mapping notation, which is the first step for all of these, this would be x minus 3 and y minus 16. Okay, there's no number in front of the 2, so there's no number in front of the y in the mapping notation. And that big 2 is part of the original function. So we can get our key point here by taking our original key point of 0, 1, plugging that into the mapping notation, and we end up with this right here, which is a key point. You might say minus 15. That's a really large number for a key point, but it happens. So we could sketch a rough graph of this. And we can say, okay, well, -3, -15, somewhere down here. Okay, we're just going to plot the point down here somewhere. We're going to make our approximation of that key point right there. And just a reminder with these, okay, there are asymptotes involved. There's a horizontal asymptote of y is equal to 0 on the original function. And then your vertical translation will move that up or down. So we know that our horizontal asymptote is actually in the mapping notation, and it's a y is equal to -16. So I'm going to draw that in right here. Y is equal to -16 is the horizontal asymptote. And from here, okay, we could sort of sketch the graph if you wanted to. But once again, okay, without the x or y intercepts, we only have that one point and an asymptote to go by. We could do it and tighten it up a little bit later, but maybe what I'll do with this one is I'll get the intercepts first, and then we can get all the other information. So let's do that, okay? Let's get a y-intercept. Y-intercept is to plug in 0 for x. So we would have y is equal to 2 to the power of 0 plus 3 minus 16. So we have 2 to the 3, which of course is equal to 8. 8 minus 16 is a negative 8. So we now have our y-intercept of 0, negative 8. Approximate it right there somewhere at negative 8. And that's another point on the graph. We could sketch our graph right now, but why don't we instead get an x-intercept, which is a little bit harder. So we can say an x-intercept is, once again, to place 0 in for y. And here, okay, we're going to have to do a little bit of algebra, but it's not logs, so it won't be so bad. I'll bring that minus 16 over. And then at this point, when solving for an exponent, you want to get the bases equal to one another. So I can set that 16 is 2 to the 4. And then at this point, the 2's can cancel, and you can solve for x. X is equal to 1. So we have our x-intercept is 1, 0. So I can put that in right here as our x-intercept at 1. And now I can sketch the graph because I have more information right here. You can see the graph looks like that, which is a translation of the original function in the upper right corner. Notice that in the mapping notation, there's no negatives in front of x or y, so there's no reflections happening. It just shifts down 16 units and has a new x and y intercept. One thing that we haven't done yet is we haven't done the domain or range, so why don't we squeeze that in right about now? The domain for all exponential functions is always all real numbers. So we don't have to think about that one. Okay, the domain is always going to be the same whenever x is an exponent, and you've already learned that in 12a. Maybe you have forgotten, okay, but that's good information to know. The range, however, is going to be different. In this case right here, we're going from a minimum of negative 16 to a maximum on the y would go up to infinity. But notice that because at negative 16 you have a horizontal asymptote, that the graph doesn't actually touch that point. So we use a round bracket for negative 16, and away we go. This is the domain and range, and we have completed this example